Okay, so we're just going to do lesson 6 problems. These are all about Gibbs free energy or just free energy. Remember, Gibbs free energy is delta G, and this tells us whether something reaction is spontaneous or not. And it's dependent on three things: delta H, temperature, and the change in entropy. So in the problems that we have here for video problem 6A, we need to know delta H and delta S. So let's look at this first one. So delta H is enthalpy or heat. So we need to look. This is giving off heat. Okay, so giving off heat means delta H is negative. Okay, now if delta H is negative, now we need to figure out what delta S is. So delta S is dependent on, right, whether we have more or less disorder. So this involves gases. So what we look at is the number of moles of gas. I don't care about the solids, it's just how much gas there is. So on this side, we have 3 moles gas. On this side, the product side, we have no moles gas. So what's happening? Well, this has more disorder. To less disorder. This has high S, this has low S. So if I'm going from high to low, that means my S is negative. Or sorry, my delta S is negative. So now this is negative, the delta S is negative. So that means this entire term is positive, right? Because I have negative and negative. So I have a negative and positive, okay? So I want to know when it's spontaneous. So when this is negative. This is only going to be negative if this term is small. So it's only going to be spontaneous at low temperature. When this term goes very small, and therefore this dominates, making it negative. All right, let's go on to D. In D now, in D we have a reaction with delta H equals 50. And let's see, our delta S is 69 joules per K. Now, we could do some calculations, but all we really care about are the signs here. So delta H is positive, delta S is positive. So that means is delta G equals delta H, which is positive, minus T delta S. So I'm going to have a positive and a negative term. So in order for the delta G to be negative, this term is going to have to be really big. Okay? So that can happen when I have high temperature, right? So this one is now spontaneous at high temperature. At low temperature, this term is going to get really small, and this is going to be bigger than this, so it's going to make it positive or non-spontaneous. Okay, let's do E. In E, we're talking about the combustion of coal. And we're told that 2C solid plus O2, C gas, goes to form 2CO. Gas. All right, so let's think about this. Delta H. In this one, I told you that heat was being given off. I didn't tell you that here. So how am I going to know what delta H is? Well, it's combustion. Why do we burn things? To produce heat. Okay? So if we're producing heat, that means delta H is going to be negative. Okay? How about delta S? For delta S, we look at the moles of gas. we have 1 mole gas here on the reactant side, 2 moles gas here. So I'm going from 1 mole to 2 mole, so my delta S is gonna, my S is increasing, so that means my delta S is gonna be positive, okay? Notice I don't care about the carbon because it's a solid. All I look for if they're gases are the number of moles of gas involved. Okay, so delta H is negative, delta H S is positive, so delta G equals delta H minus T delta S. This term will be negative, and then this will give me something. If this is positive, that means it'll be a negative plus a negative. So that means, how do I get negative delta G? Well, it's always going to be the case, because a negative number plus a negative number is always going to give me a negative. This will always be spontaneous. Okay? No matter what the temperature is, whether it's very small or very big, it's going to be spontaneous. And this is why we can always burn coal, right? If I burn coal, it's going to work whether it's negative 100 degrees outside or 200 degrees outside. Okay? All right, so let's go ahead and let's look at these again. So in these problems, the key is always to figure out what delta H and delta S are. And then you're basically seeing what happens to this T term in order, is it high T or low T? That temperature that's going to cause this. Okay, let's move on. This is video problem 6B. 6B, we're now using a different way to find delta G. Okay, and that different way is using the Gibbs free energy of formation. Okay, so delta G naught is equal to the sum N times the GFs for products minus the same thing for reactants. All right? So what we're going to do is we're going to use the values found in the back of the book in order to figure out the delta GFs for each one of these, and then we can put these all together to form the delta G. Okay, so this is plus 3H2O liquid. Okay, so they're already on the screen, and I gave them to you in the problem. So we have 0 for this, 0 for this. Why? Because these are in their standard states. The Cr2O3 is negative 1058.1. This is in kilojoules per mole. And then 3H2O, H2O liquid is negative 237.1 kilojoules per mole. You need to make sure to include or to use it for liquid water, not for gaseous water. Okay, so now I can set this up. So delta G naught is going to be, here in red, these are my reactants. Here in blue and green, these are my products. So I do my products first. Okay? So I can have 0. This is for the CR, plus 3 times that negative 237.1. And then minus, I'm going to do the same thing in red. Okay, so these are for my reactants. I get Cr2O3, so this is 1 times negative 1058.1. I have 1 here because this is 1, right? And then plus 0. Notice this is 3 times 0, which is just 0. Okay, so let's go ahead and figure this out. 3 times 237.1. This is going to get me some number, which I don't know off the top of my head. So I need to look it up. So this will be negative 711.3. Notice this is in moles. This is in kilojoules per mole. So the moles are going to cancel out and I kilojoules. Be careful about that sign. It's going to trip you up. Here, I have negative times negative, so this is going to get me positive. All right, so I have negative plus that, so that's going to get me positive 346.8 kilojoules. Okay, that is my Gibbs free energy. Okay, so we can say something about this, or changing Gibbs free energy, I should say. What does this mean? It's positive, so this is non-spontaneous. Okay? What that means is at standard conditions, this is not going to occur. Okay, so here it is on the screen. Notice that I've gone through and I colored everything by what it means to be a reactant or a product. You can see that each color, I go ahead and I multiply the coefficient times that delta GF, Gibbs free energy of formation, right? So for products minus reactants. And I get a positive number, so that is non-spontaneous. Okay, let's do one other problem. This is video problem 6C. This was the one at the very end, which I said was kind of the showstopper, right? The accumulation of all of it, right? So we want to know delta G naught, right? The change in Gibbs free energy for SO2 gas plus 2OH gas goes to form H2SO4 liquid. Okay. And we've already gone through two different ways to find delta G. One way is to use Gibbs free energies of formation. The other way is if I know delta H for this reaction and delta S for this reaction, to use those to calculate delta G. But I don't have that. What do I have instead? I have delta HFs and I have standard entropies. Okay? So this isn't quite enough. So I have negative 296.8. I have 39. And I have negative 814. Over here for standard entropies, I get 248.2. I have 183.7. By the way, always be careful whenever you write down these problems from the screen or whatever onto your piece of paper. Because I know when I did this problem earlier, I saw it on the screen and I wrote it down on my paper and I put 138.7. And I did the problem, I'm like, oh yeah. And then I looked and I'm like, wait, that's not what I got before. And these kinds of mistakes, we do them all the time because we're human, right? That's okay. But the problem is, if I'm grading the test, I can say, oh, you did something stupid. I'll give you most of the points. The computer's not going to do that, right? So we need to be very careful. Okay, so we have heats of formation. We have standard entropies. So if I could go ahead and use these to get delta H and use these to get delta S, then I could use these to get my delta G, right? Notice that this heats of formation, that's not delta H. Delta H is for the reaction. Delta HF is for each individual compound. All right, so let's go ahead and use heats of formation to find delta H. Okay, so it's always products minus reactants. So I have negative 814. This is in kilojoules, right, per mole. I'm actually multiplying it by 1 so that moles goes away. And then I'm going to subtract off negative 296.8 plus 39. Oops. 2 times 39. Why 2? Because that 2. Okay? So I go ahead and I do this calculation. I get negative 595.2 kilojoules. Multiplying this by moles basically gets rid of that. Okay? All right, so I have my delta H. Let's do the same exact thing for delta S. All right, so I can do that. Now this is 100 minus 248.2 plus 2 times 183.7. Okay? This is a minor thing, but you're never going to see standard entropies of less than 0. They're always going to be positive. The reason being is the only way to get entropy of 0 is to be at 0 Kelvin. And you can never get below 0 Kelvin, so you can never get negative values. All right, that's for standard entropies. Your delta S's can, okay? You need to be careful between those two, right? Standard entropies for one compound, delta S is for a reaction. All right, so this is going to get me negative 15.6 joules per Kelvin. Okay, multiplying by that 2 moles gets rid of the moles, but I still have Kelvin there. All right, so I have these two values. Let's go ahead and use those to find delta G. Okay, so we're going to use delta G equals delta H minus T delta S. We just found out that delta H is 595.2 negative kilojoules. And we found out that delta S is negative 515.6 joules per K. All right, we need to know one other piece of information, and that's our temperature. Well, been a little bit lazy. I've been putting them down. This knot means it's under standard conditions. So standard conditions means 298. Right? All right, so I have all three of my variables. I could put them in, but I have one other issue. This is in kilojoules. This is in joules. So I'm going to go ahead and convert this from joules, kilojoules, by dividing by 1,000. Okay? I wasn't kidding when the first day of 216 or 215, I told you that, hey, you're going to need to know these metric conversions, right? We're going to use them more. Okay, so now we're going to use this value, and we're going to plug that in. All right, so delta G naught equals negative 595.2 kilojoules minus 298K, go ahead and put parentheses around, and minus 0.5156 kilojoules per K. Okay? The Kelvin cancel out. I'm going to get kilojoules. This goes ahead, and this gets me, this is still negative 595.2 kilojoules. This now, negative times a negative, that gets me a positive. So this will give me 153.6 kilojoules. Okay? So I'm going to go ahead, take this minus, and add this, and I'm going to get negative 41.6 kilojoules. What does that mean? It's negative, so negative means it is spontaneous. Okay? And let's remember what we mean by spontaneous. Spontaneous means that this reaction up here is gonna occur, right? If I have this reaction and it's at 25 degrees C or 298 K, it's gonna occur. I don't have to do anything else to it. It's gonna occur. If it was non-spontaneous, I'd either need to give it energy or take some away in order to make it happen. Okay, so let's go ahead and look at this one more time on the screen. You can see that we went ahead, we used our heats of formation and our standard entropy to figure out delta H and delta S. We converted from joules per K to kilojoules per K. That way, when we plug these in, we got an answer in kilojoules. And then finally, it was negative, so that means it's spontaneous. All right, so that's it for lesson 6. And remember, lesson 1 through 6, that's the entirety of the information on thermodynamics, which will be the first test. All right, bye.